A very good day to Dr. Shakat. We are Group 1 and will be presenting our report on analysis and characterization of petroleum product, specifically RON 95. These are my team member, me, Hishamuddin, Naziatul, Marilyn, Hanira, Hafizi, and last but not least, Jacqueline.
Introductions. Research item number 95, RON 95 is a gasoline grade for a spark ignition engine used in the passenger cars, balancing cost and performance. Its 95 octane rating prevents the engine knocking, ensuring the efficient operation in modern high compression engines. It is popular in Malaysia, Singapore, and Europe. It meets the Euro 5 emission standard with low sulfur, supporting the eco-friendly transport. Next, we move to the description. So, chemical composition of 95, it contains the 50 to 60% alkanes, 5 to 10% alkenes, and 20 to 30% aromatics. Also, it have the additive such as ethanol, tributyl acetosaturate for stability and low emission, as confirmed by the GCMS. And then the characteristic, the Auto95 have 34.2 mJ per liter energy. The density is 720 to 775 RVP 5 to 90 kPa, and the low sulfur less than 10 ppm. FTIR show the methylene peaks at 2900 plus to 2800 plus, indicating the stable hydrocarbon. Application, it was used in the fuel cars such as SUV, motorcycle, and some generators such as ATV. So it meeting the Euro 5 standards for clean and efficient transport in Malaysia and Europe.
The main goal of this analysis is to ensure that petrol meets quality and safety standards, especially in terms of combustion efficiency and chemical stability. RON 95 contains a mix of hydrocarbons, mainly alkanes, aromatics, and olefins, as well as additives like oxygenates and detergents. To analyze such a complex mixture, we use two primary techniques, which are gas chromatography, mass spectrometry, and Fourier transform infrared spectroscopy. GCMS is highly effective for separating and identifying individual volatile compounds. We diluted the petrol in a 1:10 ratio using an hexane, filtered it through a 0.22 micromole syringe filter, and analyzed it under a fume hood to ensure safety. FTIR, on the other hand, allowed us to directly scan the undiluted petrol using the ATR crystal. These techniques identify specific molecular bonds like carbon-hydrogen bonding in alkanes and carbon-carbon double bond in aromatics. Together, these techniques provided both quantitative and structural insight into fuel sample. Here, I've broken down the role for each analytical approach used in this study. First, under chemical analysis, we focus on identifying the types and proportion of hydrocarbons and additives in RON 95. This step is crucial for predicting fuel behavior, such as volatility, knock resistance, and emission. Because of the fuel complexity, conventional wet chemistry wasn't enough, so we are going to use GCMS and FTIR for further analysis. In the instrumental analysis, GCMS played a key role in separating and identifying specific compounds. It allowed us to detect even trace levels of contaminants and distinguish between structurally similar molecules. This level of detail helps validate fuel grade and performance. Lastly, under spectroscopic analysis, FTIR offered a fast, non-destructive way to identify functional groups. For example, absorption in the 2800 and 3000 range indicates the carbon-hydrogen bonding in alkanes, while around 1600 suggests aromatic rings. This method helps confirm the presence of expected hydrocarbon types and detect any impurities or structural changes. Overall, the combination of this method gave us a complete and reliable chemical profile of the RON 95 petrol sample.
So this is FTIR analysis. Me and Hishamuddin will discuss more about FTIR analysis in discussion part.
This slide shows the result of our GCMS analysis on the RON95 fuel sample. GCMS is a powerful analytical technique used to separate, detect, and identify volatile organic compounds in a complex mixtures. The image displayed is the total ion chromatogram, or TIC, which plots the intensity of ion signals against retention time. Each peak on this graph represents a different compound present in the sample. In total, 50 compounds were detected. The major peaks correspond to hydrocarbons such as 3,5-octadiene, whereas substituted benzene, cycloalkanes, and alkane, including octane and dimethyl heptane. This compound reflects the complex hydrocarbon composition typical of commercial gasoline. Detailed identification data, including compound names and retention time, are provided in the full report.
Moving on to discussion, the objective for FTIR to discover molecular configuration and architecture of petrol RON95 by analyzing the vibrational modes of the chemical bonds that comprise a molecule. Next, to identify unique infrared absorption band linked with specific functional categories. This is the table showing the FTIR analysis of RON95 over the range of 1000 to 3000 per centimeter. Next, I will pass to Hishamuddin to discuss more about FTIR analysis.
Thank you, Nazatul. Now, let's discuss the result. Firstly, the presence of aromatic compound is confirmed by a peak at 3017.23 ref number, which corresponds to the C hash stretching vibration typically found in aromatic structure. Secondly, peaks at 1607.97 and 1493 further support this as they indicate the C double bond C stretching vibration in the aromatic rings. These findings are consistent with the literature by Stewart 2004. Next, we observe three different peaks around 2900 and 2800, which are associated with CH and ethyl group stretching vibration. This suggests presence of alkene chains in line with the work of Mausa et al. 2034. Additionally, there are no peaks detected between 2700 and 2800, indicating the absence of aldehyde group in the sample. This supports the previous observation by Nadianto et al. 2019. There are also no peaks observed in the region of 2000 to 2500, which confirm there are no carbon-carbon triple bond present in the fuel. Now, let's move on to the fingerprint region. A strong band at 1607.97 indicates the presence of conjugated C double bond, suggesting unsaturated hydrocarbon content in the fuel. Next, a distinct peak at 1493.36 confirms C double bond C stretching vibration within the aromatic rings. This observation is in agreement with Al-Gauti et al. 2008, who reported a similar peak at 1497 for aromatic structure. In addition, the 1454.21 peaks correspond to the methylene CH bending vibration, support the presence of the aliphatic component in the fuel mixture. When observing the entire spectrum, the 2800 to 3000 and 1600 to 1300 range are especially prominent. These regions are well-known signature for gasoline spectra as noted by Zia et al. 2009 and are typically associated with CH stretching and aromatic bending variation. In conclusion, the spectral profile of RON95 show a consistent pattern with gasoline-type hydrocarbon combining both aromatic and aliphatic feature, which also highlight the importance of processing and analytical modeling.
Next is discussion for GCMS. From GCMS analysis, we identify 50 distinct chemical compounds in the RON
95 sample with retention time range from 5.085 to 26.474 minutes. These compounds belong to various hydrocarbon groups including alkane, cycloalkane, alkene, and aromatic hydrocarbon. Among them, 3,5-octadiene appear as the most frequent, and insignificant concentration indicate that it is one of the dominant compounds at the peak 12. Other key compounds include cyclohexane derivative, mesethylene, ethyl benzene, indicane, and osamine. These chemicals are typical of high-octane fuel and play a vital role in achieving the necessary combustion characteristic for smooth engine operation and enhance the fuel efficiency.
In conclusion, the analysis of RON-95's gasoline using FTIR and GCMS confirms its high quality and stability for spark ignition engines. FTIR and GCMS results verify a stable composition of hydrocarbons, including alkanes, alkene, and aromatic, along with the additive like tributyl acetyl citrate, ensuring the excellent performance and profile without contaminants. With low sulfur content, less than 10 ppm, and a clean formulation, RON-95 complies with stringent Euro 5 emission standards, minimizing the environmental impact through reduced pollutants. Its robust composition supports the efficient transportation and powering vehicles in regions like Malaysia and Europe, meeting the demands of modern high compression engines and regulatory framework for clean and reliable fuel. That's all from us. Thank you.